Okay, now let's start with integrated planning in public transportation, and the first part should be about line planning. Line planning. Okay, here we are. So the main part is how to plan the lines, and as you see in this sketch, the line concept is the second step you need if you would like to set up a public transport supply. So you first have to locate stops and stations, then you can design the lines, then you can add the timetable. And then we have other planning stages that follow. And I separated this in two parts. On the left-hand side, you see things that are then only relevant for the public transport company. So for the passengers, it's not relevant what the vehicle schedules look like and what the crew schedules look like. And this is only relevant for the public transport company, but the tariff system, that is again relevant for the passengers, as also is the stops, the line concept, and the timetable. And in the end, we also have some online things like disposition in the operative business. So if you have some delays, whatever, you have to change everything which has been disturbed. So this is disposition. And in this lecture, we are dealing with the line concept. You have seen lines, a lot of lines before in Marco's lecture, and you designed your own line concept for our grid network. So you already know what lines are. And also the same is what we want to have here. So a line could be such a path through the network. This red thing is, for example, a line. And then we could have a blue line or a green line and a pink line. And what we also want to plan here are not only the lines, but also the frequencies with which they run. So if I say line plan, I only mean the lines. But if I say line concept, I mean the lines together with the frequencies. So the frequencies in this little example could be, for example, the red line would have a frequency of 2. And if you have a planning period of 1 hour, this would mean that you have a bus of red line every 30 minutes. And the pink line only has a frequency of 1, so only 1 bus per hour, and a frequency of 4. And the blue line means then a bus every 15 minutes. So, and the idea, or what I now want to talk about, is how can we model this problem to find the lines and the frequencies as mathematical program, and what could be the goals. So first of all, line planning is a problem which is well known in the literature. The first paper I know about that is from Patz in 1925. It was in Germany, in Braunschweig. And when a lot of papers followed that would not fit everything on this slide, I added some papers around 2009 to 2012, because these are two overview articles, one of Kepapsolu and Kalaftis, which is more from a traffic planning point of view with a nice list of line papers that are around, and the other one, which was written by myself, this is more from an optimization point of view. So both papers summarize research that has been done until this time, and I'm not aware of any other survey articles later on, but research still continued, and I can easily track who is working, how many people are working on that, because a lot of people are mentioning or citing my overview article, and then if I look at the citations, I automatically get a lot of new work which is around, and I added some of them. So just to show that line planning is still interesting and still many people work on that. So why do we have so many papers on line planning? And the thing is that there is not one model about line planning, but there are a lot of different models. And that's what I also want to discuss or clarify a little bit in this lecture. So let us just start and try to find a model for the line planning problem. And maybe you remember from yesterday that if you want to model a problem as an integer program or as a mathematical program, you usually proceed in 3 steps. So the first step is we want to identify the variables. The second is we want to deal with the constraints, making sure that the solution we find is feasible. And in the third step, we want to deal with the objective function. Steps 2 and 3 can be switched, but it's important to start with the variables. And in my toy examples yesterday, it was rather simple to find the variables. If you want to determine a rectangle, the variables were width and length. But now we want to determine a line concept. So what could be the variables of the line concept? And to this, what we want to find is we want to find a set of lines, meaning that we want to determine the number of lines, how many lines we have, the routes of the lines and their frequencies. But what variables would we need now to describe this problem? So describing the shape of a line, that is a lot of variables that could be used. And before we find this model, and I tell you what is the usual model and what variables are common to use in line planning, I need a little bit of notation. So the infrastructure network, Alex already introduced, also called public transport network, is the basic we work with. So we have given the stops and stations, and we have given the direct connections. That was the network you have seen in my examples here. So this basic network is called public transport or infrastructure network. And then we need our planning period T to determine the frequencies. So, and then what is a line? A line is a path in the public transportation network. A path is well defined in computer science and mathematics. The frequency of a line says how often service is offered along the line within our given time period T. So if the frequency is 1, we have two services within the 1 hour, if T is 1 hour. And the line concept is then the set of all lines together with their frequencies. So what we would like to determine is this line concept. So that consists of the lines themselves and the frequencies of the lines. But still, this is just a notation and not really a variable. So that is not an X variable or whatever. So what could we do about this? And this is done in literature by distinguishing two cases. And the way most authors proceed is that we assume that we have a line pool. A line pool is a set of lines which has been given in advance. And for companies even that, I work together with a company who designed such a line pool for German railway. So there are quite a lot of literature about how we can get a good line pool. In our research unit, the best line pools we get are from the traffic planners. So if Markus designs a line pool, that is usually a very good idea to start with that. But we need somebody who knows what lines should look like. So that is somebody who sits down and who just grabs nice paths in the public transport network and collects them in the line pool. Also in LinTim, we have a line pool from which we start. Our line pool is denoted by L0, that is the starting pool. And you see we have L1 to Ln are lines that live in the line pool. And each of these lines is a path. But if we have given such a line pool as a start, then it's easy to define the variables. Because then, similar to the knapsack problem, we can, for all the lines which are contained in the line pool, decide if we would like to choose them for our line concept or if we don't choose them. So we need a binary variable, xl, which is 1 if the line L is chosen and 0 otherwise. And instead of having this variable which is only 0, 1, it is even better just to use the frequency of the line. Because we could just, in the line pool, assign a frequency to every line. We wanted to determine the frequencies anyway. And if the frequency of such a line in the line pool is 0, then this is the same as saying this line is not chosen. And then we cannot only have 1 for choosing the line, but we can directly say the frequency would be 1, 2, 3, 4, or whatever. The other possibility would be to start with lines from scratch. So this could be modeled if you would like to have all lines. You could add all lines to the line pool. We call that full line pool because we would add all possible paths that exist in the public transport network, in the infrastructure network. And then we can proceed as with a line pool as above. The problem is if the line pool gets large, the algorithms get slow. So usually it is not a good idea to have all lines in the line pool because then our optimization algorithms would not work anymore. There are also some approaches where lines are constructed, even within the integer program. This is possible. I've shown you yesterday that we can model shortest paths or we can model paths in the language of integer programming. So we can add that we would like to look paths and have constraints that make sure that these paths are a collection of edges which are connected. So it is possible to do that within the integer program, but it again makes it very slow and it is very hard to do it in a linear way because the results have to be then modeled with variables if we choose them or not. So in this lecture, I will assume that we have already given a line pool and we will look at models that want to choose with lines out of a pool. So from now on, L0 is the given line pool, and we can use as variables either just 1 and 0 if it's only interesting to find a line plan, or the frequency if we want to deal with the frequencies of the lines. Meaning that our first step, the variables, are clarified. Now in the next step, we are not dealing with the variables, but with the constraints. So when is a line plan or a line concept, including the frequencies, feasible? And this is something where a lot of models differ. So a lot of different people have a lot of different ideas what you would like to have within the lines. And one thing which is very common in all models is the following. And this is, the only restriction which you find more or less in all models that are around in the literature. So I use that to define feasibility. And this restriction is the following. So for every edge in our network, we want to have a minimal and a maximal allowed frequency. So suppose you have one edge, maybe the street in front of your house or the street in front of a university. And then you want to say that you have a minimal frequency of buses running along the street and you have a maximal frequency. Examples for determining the minimal and the maximal frequency, or the minimal and the maximal number of vehicles, is the minimum should be the number of vehicles that you need to transport all passengers. That is also can only be approximated, but you can, if you know from the OD pairs, from where to where the passengers would like to travel, you can in the first step route the passengers just by using shortest paths, whatever. And then you see how many passengers would like to travel along every edge. And you know how many passengers fit into one bus. And if you divide that, you get the minimal number of buses you need to run along these edges. So these buses can belong to several lines, but you would like to have at least a given number of buses that go along every edge. And on the other hand, you cannot have too many buses or trains. These models work for both, for buses, for metros, and for trains, because with, for example, if you have a track-based public transport system, when you need security headways, you cannot have too many vehicles traveling along the same edge because there has to be some distance between them. Also for buses, there are restrictions for example, avoiding noise or traffic jam, so that are also often used, but you have upper bounds. And then what you require is, oh, that doesn't eat too much. You require that for every edge, these upper and lower edge frequencies are respected. So what does it mean in this formula? As variables, we already have seen that we wanted to use the frequencies of the lines as variables. So if you now want to see how many, if the number of buses along edge E fit into this interval between the minimal and maximal frequency, which is allowed for the edge, then you have to go through all lines in the line pool, and you are only interested in lines that cross our edge E. So lines that cross the edge E have to be counted, and for these lines you add the frequencies. Then you get the frequency altogether which is running along the edge E, and this frequency has to be between the given lower and upper bound. So this is the basic feasibility constraint, which can be found more or less in all line planning models which I had a look at in the literature. But also many other constraints are possible, and it is a nice homework or easy finger task to write it down, how to model these constraints. For example, people could say that they do not want more than K lines because that would be too confusing for the passengers. So when it's easy, you just have to sum up all the XL variables and make sure that this is smaller than K. Or you would not like to have more than a given number of, let's say, KV arrivals at some specific station V, because within 1 hour there's not enough space at this station, so you can only have 2 or 3 buses at the same time. Then you have just to count all the frequencies of lines that include our node V and have to restrict it. You could also say that, for example, the kilometers driven in the line concept should not be too large because you want to avoid pollution and CO2. So then you would need to look at the length of each of our lines. So since the lines are given in the line pool, you can determine the length of each line in a first step. And then you add all the lengths and multiply with the frequency. So you get the overall kilometers that are included in the line concept. And you can restrict that to be smaller than some given number. And there are many other constraints possible and also used in the literature. So these are the constraints. And you have one reason why we have so many papers are that we have so many authors. Each of the author has different constraints in mind, and also each of the author has different objective functions in mind. And this is maybe the most interesting point, because if I now give you two different line concepts, how would you compare which of them is better? You had a challenge yesterday where you designed lines yourselves, and Marcus and his group evaluated for you which line concept is better. But with evaluation is not so easy, because to evaluate this, you need to make the timetable and the public and the vehicle schedule and so on. You have to route the passengers. So these are a lot of things which cannot be included easily in an objective function. So if you now want to design a model with an objective function, which can be computed directly and linearly in the model, we need some other way to evaluate it directly. And the goals in public transport are good service for the passengers, low costs, and maybe it also should be reliable. But these goals cannot be evaluated if only the lines are known. So in our model, we are only dealing with line planning and frequencies, but we are not also designing a timetable and a vehicle schedule. We would love to do that in an integrated way. I will in the afternoon give a few hints why this is so difficult. So at the moment, we only deal with lines. So what could you imagine? What auxiliary objective functions could we use to look at only at the lines and still evaluate if they are good or bad, without using a timetable or vehicle schedule or crew schedule and things like that? Do you have any ideas? How could we, just looking at the line concept, say, oh, this could be good lines or these are maybe not so good lines? Have you any idea how we could give some approximate goal or objective function? Maybe you can write ideas in the chat or just say them into the room if you have an idea. Just open your microphone and call. Average number of transfers. That is a good idea. And saturation is maybe, what do you mean by that exactly? So probably you mean that all the edges have enough frequency. So with saturation is in some sense what we already do with minimal frequencies we want to have on every edge. So we already have some minimal frequencies and we already know that we want to have enough capacity along every edge. So this is in some sense some line saturation. Ah, you mean how many people use the line? This is also again, yes, okay. So this is a good goal that you want many people to use the line, but it is again very hard to compute if you only have the lines. You would need the passengers and route them. Okay, accessibility to public transport is also a very good thing, but we are not looking at the stations at the moment. We assume that the stations are already given and we only look at the lines. So how people get to the network is the step before. Minimize costs is a very good idea while requiring a minimum frequency at the edges. So we require the minimum frequency at the edges anyway. So we have always our constraint here. This is our constraint. So this minimum edge frequency is already required. We will have that. And this makes sure that we can transport all passengers in some sense. And minimizing cost is a good idea. That is something we will do in a minute. And if the speed is constant, minimize person kilometers traveled. This is also a good idea, but again, we need not only the variables we have so far. At the moment, we only have the FL variables or XL, which do not tell us anything about what passengers do. So there are models that include variables about the passengers, which is then gives much more opportunities and much better objective functions, but it's again also much more difficult. So these are very good ideas, and the possibilities you often also mentioned here in the chat. Thank you for that, for your participation. Are already summarized a little bit here. So something you did not mention, but that could be a goal from a passenger point of view, is to have high frequencies. So you would like to have maybe a lot of services so that people find public transport attractive. If you have this as just as goal, then you have maybe a problem that it gets too costly. So on the other hand, you have low costs. So high frequencies and low costs are two goals, and they are conflicting each other. So costs are used very often. Unfortunately, they can only be approximated. So usually you try to estimate what is the cost of a line L. You know how long the line is, how many kilometers. You can, in some sense, approximate how many driving kilometers you have and how much time you need if you drive this line. So you can approximate the costs that are needed for the driver, for the time he needs, and the kilometer for the car. So you can approximate the costs and try to minimize that. Few transfers. Oh, it should not be few transfers, should be many transfers, by the way. We would like to have a lot of, few transfers is correct. Sorry about that. We do not want to have the passengers needing to transfer too often. Passengers would like to have direct lines. So we would like to have few transfers. This can be modeled. I will show you in a few minutes. Small approximated traveling time. This is maybe the best we can do, but we already find an approximation what the traveling time for passengers is, because most passengers would like to have a fast transportation, and also many direct passengers can be modeled. And also the ideas you have can be added to these objective functions, and this again explains that you have so many papers. So you can have, for example, a paper dealing with the costs. Then you would have a cost model. This model tries to minimize the costs, but in the constraints requires that you have a good quality in the service. You can have an extended cost model where you have the costs modeled more detailed. Then you could try to maximize the number of travelers who can travel directly. To maximize those, you would like to add as many lines as possible. So you again have to use now a bound on the costs to restrict the costs. And in the travel time model, you would like to minimize the average travel time for the passengers. And again, this would be possible if you established all lines that are in the line pool with a high frequency. So you also need some constraints that have an eye on the budget. And these are 4 models that are rather common in the literature, but there are a lot of other models, and each of the authors has maybe a little bit changed the objective or a little bit changed the constraints to the needs of a problem he already looked at or to his subjective needs. So that explains why you have such a mass of papers on line planning. Okay, now I want, in the end of this lecture, give you a short insight into these models. And yeah, I started a little bit later, but I think we can do that rather quickly, just to give you the idea how these models look like. And this is also my main message about line planning. Line planning has a lot to do with modeling, because all these papers, they differ mainly in the models. Some of them are rather easy to solve. You will see in LinTim that the cost model, for example, can be solved within seconds, even for large examples. So it's very easy to solve them, but it's very important what the constraints and the objective function are. And it's always what you get is what you put in. So if you tell your model you would like to have small costs, the model tries to reduce the frequencies as much as possible and just respecting what you want to see. And that is the first we want to have a look at. First of all, just let's have a look at the costs. The first observation is that we cannot really compute the costs if we only are at the line planning stage, because a lot of costs come from the vehicle schedule. We will discuss vehicle schedules later today, and we will see that it's very important to have not too many vehicles and that the vehicles have not too many empty kilometers. But this is a separate optimization problem. And also the crew scheduling problem is a separate optimization problem. And both of these problems determine the costs you will have. So this cannot be done in line planning. And the only thing we can do is something that uses the XL or the FL variables. And what can we do to approximate at least the costs? We want to look at the cost types we have. We have usually costs per time, because if we drive with a line, with a bus, we have to pay the driver, for example. And we have costs per kilometer, because we need gasoline and the tires, and also the car gets has to be, is used if the bus is used if you drive with a bus. And so what we can do is we can, for every line, determine how much time we need to drive this line and how long the line is, and multiply with the costs per time and the costs per kilometer. And when we get something, a cost coefficient per line, so that is this cost L here. And if you have a frequency of 1, then you only once have this cost, but if the frequency is high, you have to multiply with the frequency. The good thing is, if you start with a line pool, you can determine these cost coefficients beforehand. And for the line pools in LinTim, we have these cost coefficients such that we can, if we use them. If you construct the lines from scratch as paths in the public transport network, this is a bit more difficult, because you cannot use such cost coefficients for every line if you not even have constructed that. But you can use some formulas, for example, some type of fixed cost, and then you can measure how long the lines are that you construct and what the time is. So you can also use that, do that within a formula. But for our purposes, we start with these cost coefficients per line. And then the model is rather easy. So this is the cost-oriented line concept, where we have given the upper and the lower edge frequencies. And we look for a line concept that minimizes the overall costs. And the costs is just given by summing up the costs for each line, multiplying with the frequency, and summing over all lines. So if we want to minimize the costs, then it would, as you also see in this formula, and which is also very intuitive, you will get lower costs if you have less lines. So if you just want to minimize the costs, it would be best to have no line running at all. So you would set all frequencies to 0, and then you have 0 costs. This would be a solution, maybe the best solution if you look at the costs. So this tells you that in our constraints, the lower frequencies get very important, because the lower frequencies make sure that you have enough service along every edge. So the lower frequencies forbid you to put all line frequencies to 0. And they ensure that you have a good quality. And if you route passengers along shortest paths in the beginning, then the lower frequencies even give you a very good service quality. So this is now the cost model that comes out of the thing. Here is our objective function we have already seen. Here are our constraints. These are the same constraints we had before, but written in 2 constraints. So for every edge, we want to make sure that we have enough frequency along the edge, which can be done by going through all lines in the line pool, which contain our edge E, and adding up the frequencies. And we also might have upper bounds, making sure that we have not too much lines along the same edge. And the variables are the frequencies, which are natural numbers, so 0, 1, 2, 3, and so on. And if we have found the frequencies, then we can easily find also the line concept, because all lines with positive frequencies have to be established and all others are not needed. So now we can analyze this problem, and I'm not going into detail here. First of all, it's interesting to see that it is one of the hard problems. So if you have a lot of lines, then it will get slow to compute that. And that's what I already said. If the line pool is too large, then the algorithms will get very slow. And interestingly, from a mathematical or computer science point of view, the problem is strongly related to something which is known very well and which is called multi-covering problem. And this is the case if you have no upper frequencies, then you can solve it as a covering problem, which is a good basis for designing algorithms. That is the cost model. And then you have any questions about the cost model? This is also the model we use as a standard approach in LinTim, so you can try out what happens if you use the cost model. The cost model can be extended. We have seen that the cost model is very basic, so we have only a very basic approximation of the costs. But if you really would like to do line planning in practice, you would have different types of vehicles, like big or small buses. Maybe you want even to plan not only buses, but also metros in the same problem. So you have different types of vehicles that have different capacities. And in rail transportation, you also have, for example, to decide how many cars a train should have, or how many cars a tram should have. So if you would like to include more parameters in the costs, for example, fixed costs per car of type T, costs per kilometer with a car of type T, so you can have different types. A larger bus is more expensive than a smaller bus. It also might have more costs per kilometer. The capacities depend on the type, and the number of cars that are allowed for different train types might also be different. So you can include a lot of other parameters if you like. Then you need also more interesting variables. So the variable is then not only if you would like to use line L or not, but you have to include the type and the car, for example. So you have a variable with 3 indices. XLTZ is 1 if line L is served by vehicles of type T with exactly Z cars and 0 otherwise. So these are many more variables because you have 3 indices. And then you can add everything up to some objective function that minimizes costs. And you even will have a quadratic term in the objective because you multiply our variable with the frequencies later on. So that's what you see here, FL times our variable. That's a multiplication of 2 variables, which is bad. So to avoid this, we even need to have 1 more index in our variables. Now the frequency goes as index in our X variables, and such an X variable is 1 only if the line L is served by vehicles of type T with Z cars and frequency F. So you see most of these variables will be 0 anyway, but you need a large number of variables, making the problem not so nice to compute. But you can, and the problem looks ugly like here, you recognize our constraint, which is in all models, like the minimal and the maximal frequency should be respected. But everything is now with much more complicated variables. The model gets more complicated, but the costs get more realistic. So you can decide how realistic you would like to be and how much runtime you have. So this is a possible way to extend the costs and to compute everything more detailed. And then we have 2 models that deal with the passengers. And this first is the direct travelers model, and the second is the travel time model. So for the direct travelers model, we would like to maximize the number of passengers that can travel directly. So we call a direct traveler a passenger who do not need to change the line on his or her journey. And the goal now is to design the lines in such a way that as many passengers as possible have a direct connection, meaning we would like to maximize the number of direct travelers. So now we only have as variables so far our FL variables, the frequencies. Alone from the frequencies, it's very hard to compute the number of direct travelers. So we need some tricks to determine this number of direct travelers within the model. And for this, we have an assumption that passengers use preferable paths, and these paths should be known beforehand for every OD pair. And then we can determine if such a preferable path, for every segment of a line or for every path between I and J, should be a shortest or preferable path between the 2 stations I and J. And we can, for every line in our line pool, determine if such a preferable path is included in the line or not. So for example, if we have this line, black line, from 1 to 5, we see that this path from 2 to 3, maybe some passengers would like to travel from 2 to 3, that is definitely a preferable path for them, and it is contained in the line. But P14, there's also a preferable path contained in this line. Also, there exists another one, but this one is preferable and it's contained. But for example, the path from 1 to 5, which is maybe much shorter, going this way when taking the line L, it would not be contained in the line L. Also, passengers could travel directly between 1 and 5. If it takes too long, it's not the preferable path, so this is not counted. And using this trick of preferable paths, we can now define a model, and we use the old variables, the frequencies, but we have a new class of variables that we have to use. And this variable has 3 indices again, so D, I, J, L, and it denotes the number of direct travelers between stations I and J that use the line L. So if we establish the line L, we can count how many passengers travel directly. And this is now that we sum up over all these variables D, I, J, L, looking at all stations I and J, all lines and all preferable paths belonging to such a line to count the number of direct travelers. So we need this 3-index variable to count the number of direct travelers. The constraints are not so easy because it's easy to write down what I understand what DIJL should be, but it has to be something that comes out of our program. So we have to find a mathematical program and constraints that really compute the DIJL in such a way that they fit to what I want to have from them, that they in the end count the number of direct travelers between I and J that use the line L. But this can be done, and it's due to Busiek, who first established this model. And again, you find our frequency constraints that we have seen beforehand. And in this case, the upper frequencies are very important, because if you would like to maximize the number of direct travelers, you would tend to have as many lines as possible. And these are now the restriction that you cannot have too many lines, so you are not too costly and not overcrowded. The problem is again NP-hard, and there are solution approaches that deal with aggregation. Finally, a few words to the travel time model before Alex stops me. The travel time model is interesting because it goes in the direction that we have to include the passengers in a better way. And that's the main message I want to transfer here, that passengers choose their paths dependent on the line concept, but the line concept is something we just want to compute. So more precisely, a passenger chooses a specific path if it is short, if it has few transfers, if a service is offered very often, so if it has a high frequency. You have seen all these things in the lectures on Monday and Tuesday morning. But these properties, if the path, the route the passenger chooses is short, if it has few transfers, and how the frequency is of this route, this cannot be known beforehand because this depends on the line concept, and we want to determine the line concept. So in some sense, we have a chicken and egg causality dilemma. We could start with a transportation system, and then we can determine the best paths for the passengers. Or we could first start with the passengers and use then the data how many passengers use which edge for determining the line system. So in some sense, we have to start with one point, and we even can go around in circles. But what we do here is we want to combine both optimization problems to one. And yeah, the question which paths passengers like, if passengers would like to minimize riding time, you would like to have a lot of direct short connections. If passengers would mainly deal with having no transfers, then maybe one line going through all the stations would be best, because everybody can travel in this line concept without any transfer. But as you easily see, the thing that you really want to have is somewhere in between, because nobody would like to travel all this detour only because he need not change. And otherwise, passengers also would not like to change too often. So what we did in line planning is we wanted to take both effects into account. And this is the approximated travel time, where we look at the riding time. That is the only time we can compute for the line concept, because we know how long each line in the line pool needs for every edge. And we give a weight how important this riding time is for us. And we can count the number of transfers. And we give another weight how important the transfers are for us. So We could take this weight as estimate for the average waiting time and changing, but we can also say transfers are inconvenient. We can even have a larger weight. So the nice idea is if we take both of these effects into account and we want to, in the end, we want to minimize this approximated travel time over all passengers, then we can, if we have a large K1 compared to K2, then we will have that we have only a small riding time, but passengers might have a lot of transfers. If we have a large weight K2 and a small weight K1, then we would minimize the transfers. And this is then the so-called travel time model, where we look for a line concept that minimizes all this, the sum of these travel times, these approximated travel times, and having a constraint that makes sure that the costs are not too high. Now, this can also be modeled, but this is maybe now too long because Alex wants to continue. This model is a bit harder to compute because we have variables for every OD pair. We need also one more construction, namely what we call change and go graph, where we can take count of the transfers between different lines and give some weights to them. And then we can use some shortest path procedure in between the model. So I've showed you yesterday that we can model shortest paths as integer program. So we need exactly such variables to model a shortest path for every OD pair from S to T. And if we do so, then all these shortest path constraints are summarized in something which looks very simple, but it contains a lot of constraints, namely making sure that every OD pair travels on a shortest path with respect to the line concept that we want to establish. We have our cost constraint and the variables we have, that is what we see here. So we need new variables. We need that something like the frequency that we use the line L or not, and all the shortest paths. Yeah, so this can also be done if you want to use frequencies instead of just saying a line is used or not. And it is also NP hard and is often can be solved by Danzig-Wolf decomposition. That's what I wanted to say here. In principle, you just can take as take-home message, whenever you include the OD pairs and the passengers, the model gets more complicated and more difficult to solve. And I thank you for your attention and pass over to Alex with a 4-minute delay. But I also started with some announcement, Alex, so don't be too strict with me.
Yeah, no worries. So I would say you're definitely in line for the 45 minutes. Okay. Yeah, regarding the rest of the session, so I would like Alex to open up the breakout sessions again. We would like you to go back into the rooms you were before, so just use, we did some real-life scheduling, so or rescheduling, so just go into the group that you were before. Hopefully this will work out, otherwise we will come to you and see if we can merge some groups or stuff like that. And we would like you to have a look at the exercise sheet 02 line planning. You can find that in the C file downloads. Yeah, where you will play around with different cost models, different direct models on different data sets, and just play around a little bit, seeing how does the models perform on different data sets, how does different models perform on the same data sets, and just play around with it a little bit. We'll see how far you get. I think we will meet in around about 35 minutes back here. And we will probably just close the breakout sessions again, so you will have no chance as to come back here and cannot remain in your groups. And I will give you just a 2-3 minutes idea of what were the things that you should have seen. You can maybe give us a little bit feedback of what you have seen, that we just make a 5 to 10 minutes feedback round, and then you can start in your lunch break afterwards. So I hope all of you had a little bit of a chance to play around with LinTim a little bit, with the line concepts, create some line concept with the different models that we've seen. And I now just want to take 2 or 3 minutes, so really not too long of your lunch break, to just give you an idea of what I would have liked to have that you've seen, and we see how far this is the same. Okay, first of all, for the cost-oriented line planning, I just added some evaluations here. These are the evaluations on my machine where I compared the runtime with the costs. And I just want to mainly focus on two things here. So you compared the cost algorithm with the different greedy heuristics. And first of all, or there are a few things that you can see here. First of all, most of you got some warnings and were somehow confused. Well, this is infeasible. This seems to be infeasible. Yeah, that's definitely true, and that's the correct way to how it should be. Because these greedy heuristics are fast, and they are fast because they don't solve the line planning problem correctly. They are just a heuristic. So what they will do is they ignore the upper bounds. They have a frequency bound that Anita showed you in the example. And that's the reason, because even finding a feasible line concept, just respecting the lower and upper bounds, is an NP-hard problem, so that's in theory hard to do. So these greedy heuristics are fast. That's something that we see here. For example, half a second in comparison to 0.04 seconds. But they won't provide you in all cases with a feasible line concept. And another thing that we see is that the costs are often higher, right? So we have more or less double, or here even a higher amount. Here's, I think, the biggest example was, I don't know, some kind of 5 times the amount of costs that we get when using the greedy heuristics. But the trade-off is it's fast. You may discuss if it's reasonable or not, because, well, okay, yeah, it's faster than cost, but cost needs 2.5 seconds. So maybe it's not that important. But of course, this is always the case for heuristics, that they may not find the optimal solution, and they hopefully are a little bit faster. Well, the second one, the direct travelers. Yeah, just a very similar observation that we can do here. So comparing the direct model with the direct relaxation. The relaxation works faster, but it's not as good. Again, you just observe the trade-off, especially for the larger data sets. So I let you try, or you could try it out on barn 01, where, well, at least the direct model needs 20 seconds. So that's not very fast, but the relaxation is much faster, but does not find the optimal solution. But you may have data sets where it finds the optimal solution, right? So on the first data sets, on the smallest data set, the relaxation works as well. So there may be data sets where you don't need the exact model, but an easier to solve model is good enough. Yeah, setting a budget. I just gave you a short here. I didn't put too much time into drawing this. You can probably do it better. But just to give you a short insight here. So up here we have this small, yeah, it's kind of a curve. You could probably draw a line from here to here. This is the cost optimal solution that you can compute without setting anything. It is very cheap, but does not have too many direct travelers. Setting a budget, or just computing direct travelers, more or less will approximate this curve here, right? Increasing the costs will allow me, or increasing the budget will allow me to support more direct travelers. And you can a little bit see what happens here. This is the nice thing when you don't have to be feasible. So this cost greedy heuristics things here are not too costly, but have very, very high direct travelers. And this is just mainly due to being infeasible. So they do not solve the original problem. And the last thing that I wanted you to see, or that you could see, is what happens if you try different line pools. So don't look at this configuration stuff in here. That's morely that I remember which configuration I set to create this line concept and this line pool. But the line pool generation has different parameters. You can play around with them and create different line concepts. And you really see that that's important. So everything is modeled, is optimized either to costs or to the direct travelers. And you see here, if you just use the default parameters, you get an optimal cost of 631. But if you plug in a bad line pool, for example, just using the k shortest path problem, so I just add shortest path to the line pool and not look at other ways to do that, my optimal costs are nearly doubled compared to the real line pool. Yeah, so main topic is the line pool generation is important. And you should have a look at it if you're looking at line planning in practice. It's not so easy to find good lines. Okay. And with that, I don't want to steal you too much of your lunch break. If you have any questions regarding usage of virtual machines, something is not working yet, you got strange error messages whatsoever, and I couldn't get to you in time during the last exercise session, feel free to stay a few minutes longer. I will stay in here for a few minutes and see if anyone else has questions. Otherwise, I wish you a very refreshing lunch break, and we will meet again in 45 minutes to hear a little bit about timetabling and see what happens there.